Okay, and what I want to talk about one more time is this last question here. Determine the temperature range in which the reaction is spontaneous, right? And that has to do with the signs of the delta H and the delta S, okay? Now, just to fix it, because we couldn't find the thermodynamic data for a solid, we turned that into a gas, correct? And we would have had some delta H and delta S information, and I'm just going to ask you for that right now. What was the delta H? Yep. Negative 44? Negative 44 kilojoules per mole. And what was the delta S? Yep. Negative 118.9 joules per Kelvin mole. And in the end, we took our delta G equals delta H negative T delta S, and we let the delta G be equal to 0, right? And that when we let it be equal to 0, when we do that, again, I'm reminding you that this is our condition for that reversible reaction, all right? So this makes it reversible. So determine if it is reversible, determine the equilibrium temperature. That makes it reversible. Reversible, you get the idea, all right? So then we rearrange, bring this to the other side, bring the T down, and when we do that, we bring that over there, we end up with T is equal to delta H over delta S, right? Does that sound familiar? Yeah, don't mind that scribbling up there, cheapers. Have to have it in the same units. We ended up with a temperature, I believe, of what, 370 Kelvin. All right. This is essentially the boiling point of the liquid, because when you have a phase change at that boiling point, at that phase change temperature, you actually have this reversible situation. Some of it's condensing, some of it's boiling, and you've got this reaction battling back and forth. If you make it hotter than that temperature, then one of the reactions wins. And if you make it cooler than that temperature, one of the other reaction wins. It heads back to the other way. All right? Okay. So now we're to the point where we want to talk about this. Determine the temperature range in which the reaction is spontaneous. All right? Now, I do have a couple of notes, and I had you write some stuff down there in the middle of the question, which might be a little confusing. So let's write this down a little more officially. Please write the top box. And then I am going to amend this bottom part, but don't write it down. Just write the top box. All right? Remember from the equation, the temperature affects the entropy. If we have a temperature that's lower than the equilibrium temperature, and that's what we found, 370, then that entropy term shrinks and becomes less of a factor. So to determine the spontaneity at temperatures below the equilibrium temperature, you're looking at the delta H. Because at temperatures below the equilibrium temperature, the entropy term shrinks, and this dominates the calculation to get the delta G. From our reaction we did yesterday, and I had to change this because I was having it going from solid to a liquid, and that changes the sign of everything, but it's not a big deal. But our delta H was less than 0, it was negative, and our delta S was less than 0 as well, it was negative. At temperatures below the equilibrium temperature, we're looking at delta H. Is a negative delta H supported by the universe? Does the universe like a negative delta H? The answer is yes. So because the delta H is negative, at temperatures lower than the equilibrium temperature, it will be spontaneous. So when the temperature is below 370, look at the delta H, therefore, yes, spontaneous. So I don't know what you want to write for that. You could write this whole thing if you'd like, if you want, if that's going to clarify things for you, all right? We've already got that reaction up above. We've got all the numbers right there in your question up above, so maybe you don't need to rewrite it. But at temperatures below, look at the delta H. So if the delta H is spontaneous, then that reaction is spontaneous. All right? My next slide's going to have the exact, yep.
So that's when the delta H is spontaneous, that's when you don't even figure out delta G because you know it's just
You don't need to figure out delta G. We actually aren't figuring out delta G to do this. We don't have to do that.
No, but I think I do that. Say like delta H was like negative, that means spontaneous, so that's kind of G.
Was there a question where you had to find some delta G's and delta S's and delta H's? I don't understand the question because I don't think there's a situation where I'd ask you to do that. All right? When we get to doing the homework, I'll come and address that specifically, the question that you have. If we did have a temperature below 370 and we did want to stick it in this equation, right, then this would become small and my delta H or my delta G would become the same sign as this, and it would be negative in this case. So we would get a negative delta G. And remember, negative delta G's are spontaneous. So this makes this spontaneous. Okay? For the flip side, at temperatures higher than the equilibrium temperature, we say they're entropy driven. Because now this term, the entropy term, grows larger than the delta H term. Again, this is gas because we changed it. We have here less than 0, and the temperature we're looking at here is 370 Kelvin. So when we have temperatures above the equilibrium temperature, we're looking at the delta S. This is true for all equilibrium ones, whether they're both up or both down, right? But depending on which way the delta S and the delta H is, that's what's going to determine where your spontaneity is. So in this case, when the temperature is above delta S, we're looking, or above the equilibrium temperature, we're looking at the delta S. So since the delta S is negative, what does the universe think about entropy decreasing? Does it like it? No, that's becoming more ordered. So since delta S is less than 0, therefore non-spawn, all right? Not spontaneous. Okay? All phase changes are like this. All changes of state will be a situation where they're both up or they're both down. Because all changes of state, to go from, say, a gas to a liquid in this case, since we're going from a high energy state down to a liquid where they're moving less, that will always be a decrease in enthalpy. But going from a disordered gas to a ordered liquid will also be a decrease in entropy. All changes of state will have the same sign depending on which way you're heading. All right? It'll either be gaining in energy, but it'll become more disordered, or you'll either be going to less energy, but it'll be becoming more ordered, which means all changes of state will have an equilibrium temperature, which is the temperature for that change of state, the boiling point, the melting point. All right? There was a question I kind of ignored. Yep. When they're both the same sign. As soon as you've got that, it's either always spontaneous or always non-spontaneous over the entire temperature range. You cannot make that delta G become the opposite sign no matter what you do to the temperature. And we'll hopefully one of my examples deals with that. If not, we'll talk about one of the questions on the thing. Let's go back, though, one more time to this question here. Determine the temperature range in which the reaction is spontaneous. We can flip this thing on its head. What I've told you to do at this point is, I've said, okay, if the temperature is below it, it's enthalpy driven, and if the temperature is above it, it's entropy driven, right? So why don't we flip it on its head in order to answer the question? Determine the temperature range in which the reaction is spontaneous. Why don't we go to the delta H and delta S and ask ourselves the question, which one of these properties is the spontaneous one? So instead of thinking about above or below the temperature first, go back to the question and ask yourselves, which of the thermodynamic properties is supporting spontaneity? Which one is it? Which one is telling us that it's spontaneous? Yep. The delta H is, because it's negative. So then we can go back to the equation and ask ourselves, what has to happen to the T in order to make the delta H dominate this equation? What has to happen to the T in order to make the delta H the big number in this equation? If the temperature gets higher, then this term grows. And this term, this mathematical term, will dominate over that. So the answer is no. All right? Because if we want it to be spontaneous, we want this number to be dominating the mathematical equation. We want this number to disappear and become minuscule, tiny. The way we make this number disappear, this is a constant. It's the number that we just calculated. I can manipulate this. If I want that number to disappear, I've got to make the T become smaller. So by flipping it on its head, you're going to say to yourself, all right, I want to know the temperature range in which it's going to be spontaneous. The delta H is spontaneous. In order for this to dominate, the temperature's got to go down. So we would say then that from 370 degrees and down, this is a spontaneous reaction. Right? And that's flipping it on its head. I think that even that makes it a little easier, but maybe it doesn't. In my mind it does, but if you like the other way, that's fine. And then let's think about this logically. This is the condensation of water from a gas to a liquid. When does water automatically condense from a gas to a liquid? Well, below the boiling point. And that's what we've thermodynamically supported. Below this temperature, this dominates, and it will be spontaneous. It will condense. All right? Let's look at a whole new problem here. Hopefully we can come up with one that has some different values here, and then we can make some sense out of it. Same type problem. Exactly the same problem, except we just have a new chemical reaction. So, go through the same motions. I'm really hoping that my example has all the information on the thermodynamic table so we don't have to Google away. Wouldn't that be great? I should give you a test without any thermodynamic data, and you've got to bring your smartphone and look up every piece of data. No, that wouldn't be fun. Everybody doing their thing. And we're getting pretty good at this thing. I will just take your final delta H and your final delta S at this point when you're done that. Yep. We're missing something? Oh.
The delta H is negative 176.
176? I thought we were missing data already. Negative 176 kilojoules per mole. Units are incredibly important in this because we've got to change that delta S or you'll get some absurd numbers. You got delta S as well?
Negative 0.2848.
2848 kilojoules. Oh, you already moved it over. That's exciting. Kilojoules per Kelvin mole because we've got to multiply it by the T. So coming out of the equation, you were getting 200. Negative 284.8 joules per Kelvin mole. Now, this is the exact same situation as it was a moment ago because it's a negative and negative. And the reason for that is because my first example, which was solid to liquid, should have been positive to positive, but I couldn't find the solid data, so I switched it to a different change of state. You see what I mean? Solid to liquid would be going from low energy up. Gas to liquid is up to down, so I've got the same type situation. It's not a new scenario, but anyway, we can still do it. Do we like these numbers? I really hope someone else is actually checking and calculating these. We want support by committee. Support? Supporters? No? Yes? Nothing? Oh, calculators in the dark. What type of calculator do you own? A Casio. That's a piece of junk. That's why you're having troubles. Casio. Get yourself a Sharp. Casio can make a nice watch or two, but can't compete in the calculator world. Support? You like it? All right. So then the question becomes, is the reaction spontaneous, non-spontaneous, or reversible, right? And again, if I've got that negative delta H, positive delta S, spontaneous over all temperatures. That's what the question was, and I don't know if I have an example. I'm not going to have an example for this because it's not that exciting.
That's mine.
That's cool. Is that the phone ringing?
No, that's my alarm.
Oh. Turned off? That's all right. That's neat. That was fun. See the distraction? It's amazing. Okay, let us refocus. All right. So, if we have, right, a situation where they're opposite, then it means there's no temperature that you can solve. This isn't opposite. These are the same sign, which means we're going to have to go through the motions. But I just want to stress. If you come across one, like in number 2, if you did for homework, right, you have negative delta H, positive delta S, then your answer to this is that it's spontaneous. And if it asks for the temperature, if it asks for the reversible equilibrium temperature, not available, not applicable. You can't find an equilibrium temperature if they're like that, all right? And if it asks what's the temperature range for being spontaneous, if they're both supporting spontaneity over all temperatures. The reaction is always spontaneous over all temperatures is your answer, all right? If you've got it such that it's the other way around and they're not supporting spontaneity, then the reaction is non-spontaneous, all right? Reversible temperature, no, not applicable. You cannot find one. Determine the temperature range. Over no temperatures is that reaction spontaneous. It's never spontaneous. Doesn't matter what the temperature of the reaction is, okay? Now in this case, we've got both down, which means we will have an equilibrium temperature. If it's both up, we will also have an equilibrium temperature. So the answer to A is down, down, it's reversible, right? Therefore reversible. They have the same sign. One's pushing one way, one's pushing the other way. Determine the equilibrium temperature. You might even remember that equation without having to resolve it. What is the equilibrium temperature equation? T is equal to delta H over delta S. You could memorize that if you want, but it simply comes from here. When we make that delta G 0. Negative 176 kilojoules per mole, negative 0.2848, and that is also kilojoules per Kelvin mole. The moles are gone, the kilojoules are gone, Kelvin swings up top, and you get a Kelvin temperature. If you think about it, if they were opposite signs, then one of these drops off, and you get a negative temperature. There's no negative Kelvin temperatures, folks. That's against the rules. And so if you get a negative Kelvin temperature, you've kind of zoned out and started to do the question, and you really shouldn't have been able to do it. You actually have a non-spontaneous or spontaneous overall temperature situation going on. What do we have there for the temperature? Yep. 618 Kelvin. This is a chemical reaction. It doesn't have meaning like boiling or melting, but that's the temperature at which it becomes spontaneous in one direction or shifts back to the reactants to the other direction. At this temperature, they're heading back and forth nicely at the same speed. Okay. We've determined the equilibrium temperature. C. Determine the temperature range in which it becomes spontaneous. Again, this is this whole discussion about above the equilibrium temperature, this dominates, below, this dominates, and that works. But if we're looking for the temperature for where it's spontaneous, if we flip it on its head, which one of these thermodynamic terms supports a spontaneous reaction? Which one? Yep. The delta H, all right? So, for C, delta H is spontaneous. Therefore, what do I want the temperature in this equation to be such that the delta H dominates? Yep, lower, because then this is small and disappears away, and this dominates and contributes to the spontaneous. Therefore, T needs to be small. We don't need to write that, I guess, right? I guess at this point, once you determine it's lower, you can say 600, less than 618 degrees, right? 618 degrees and down, you know what I mean? And below, so temperatures below, up to 600. How do we want to write this? Yeah. T, less than sign, 618, less than or equal to. Oh wait, no, that's right. No, not equal to, because if it's equal to, it's reversible. Look at how far you guys have come with your less than signs. As a teacher, that makes me so happy. Remember we struggled with the less than? Yeah, that was fun. I like making fun of that for you guys. And you just got me back there. That's good. Nice job. I struggled with my less than sign. Does this make a little more sense than it did yesterday as I was freaking out with 10 minutes left to go in class? Yep. Yeah, it would not be spontaneous. The reaction would not happen as written as that. It actually would happen in the reverse scenario, so everything would shift back this way and we'd be back to products. In other words, we call that a non-spontaneous reaction. Yeah. Or the opposite reaction becomes spontaneous, right? Because if you think about it, if you flip the whole equation around, right, the signs change everything here, and then you've got spontaneous above that temperature. It comes back to the front end. Okay? All right? One more type of question, and I found this type of question, and I do like it because of its simplicity, yet it's complex. And I do have an example of it on the worksheet, so I just wanted to talk about it. And I haven't done a question like this before. I saw the question, I thought, that's pretty neat. That's a neat way to ask that question. So, very simple, elegant question. Determine the melting point of sulfur using thermodynamic data. And I guess the big thing we need to realize here is that when you have a change of state, you're going to have the same signs, depending on which way you're going, of the delta H and the delta S, which we can put in our equation, and we can get that equilibrium temperature, because that equilibrium temperature is where melting dominates or freezing dominates, all right? So we need a simple little equation for sulfur. What's the equation for melting or freezing? It doesn't matter which one you pick. You'll still get the same temperature, yep? Sulfur solid to sulfur liquid. You could have done it the other way around. It still would get you the right temperature. It would just change the spontaneity thing. So we need a delta H and a delta S. Come on, are you kidding me? When I made this question up, I looked at the data sheet. Really? No way. I'm checking again. I don't believe you guys. S. Son of a gun! Solid in a gas! I'm looking it up. We're doing this question. It kills me. Look, I'm alt-tabbing. I don't even know where I'm going anymore. I'm just alt-tabbing. What do we want? Entropy of formation of sulfur liquid. Liquid. Come on. Standard mole of entropies. Solid. Oh, this is sucking. I'm not getting anything here. Oh, look at it's putting. Oh, we got to put sulfur. It's going to take forever. Jeez. Sulfur. Yeah, it'll fix it for me. You break. Sulfur. Blah 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 blah. Delta H formation of the liquid. 1.85 kilojoules per mole. Entropy of the liquid. 36.8. Okay, we got it right there. Let's zoom in. Boom. Right there. There's our data. Oh. I don't even know what the melting point of sulfur is. This is going to be fun. This is fun, people. All right, what do we need to do? We need the liquid, which is the data we're looking for. Negative. Oh, sorry. I flipped it around. We go negative the solid plus the number for the liquid. Negative solid plus the number for the liquid. What is that liquid, or sorry, that solid number? element in its standard state, of course. Why you guys gotta be so mean to me? Holy cow! All right. I've been frazzled by the 1.85 liquid, solid, negative. No, I can't do math either. 1.85 kilojoules per mole. Starting to sweat. 36.8. 5. This one isn't 0. 31.8. 31.8. All right. Which means we're going to get a positive, right? Yeah. What is that number? 5.05? 05 joules, right? Joules per mole Kelvin is the way they've done it. Okay, excellent. Equilibrium temperature. Delta H over delta S. Delta H, 1.85. And that's kilojoules per mole, which means we've got to move that over 1, 2, 3, right? And that's going to become 0. And then 0.00505 kilojoules per mole. Almost there. This should have a melting point on it as well, doesn't it? Blah, blah, blah. Temperature, what is this? The table, solid phase, heat capacities, nope. Not even a melting point? Yeah, sometimes they'll just do an MP on you. It's just thermodynamic data, molecular weight, CAS, blah, 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 blah. Oh, well. No, it's okay. I didn't see it anyway. Okay, what do we got for a number? Yep. 363 Kelvin. 366 Kelvin. What is that in degrees Celsius? Just I'm curious. 93 degrees Celsius to melt it? Huh. I didn't know that. That's pretty cool. Let's just finish the logic here since we've got a positive and a positive. If I want to know the temperature range in which this is spontaneous, all right, which of the thermodynamic data do I have to look at? Yep. Yeah, the delta S is positive. So delta S is spontaneous in this case. So what temperature does the temperature have to be for it to be spontaneous? Yeah, so T greater than 366 Kelvin, it'll be spontaneous. And this is a melting situation, right? You heat things up in order for them to melt, all right? What do we got here? Melting. Is it? Yeah, of course it is. What the heck's going on here? Silly. It's all there. Sulfur 112. So this is the thermodynamic data. This involves, the reason it's different will involve the scenario in which it's measured. Again, these are usually approximate, but don't sweat about it. That's a good number. All right. That's a good question. I like that question. Let's keep going now and talk about criteria for spontaneity. I already have it on this chart here, but I want you to write it down in terms of delta G. And there's no way I'm going to get done this lesson quickly, so tomorrow will be a full review period. I will get done this lesson, but I mean quickly in order to get my next lesson in. So we've been looking at temperature of spontaneity by comparing the S and the delta H. But there is another way to calculate the delta G, all on its own. And that is using a standard table of Gibbs energy, which is on our table. We have a delta G column on our thermodynamic data sheet. Again, here this just kind of reviews what the delta G stands for. If it's negative, yes, it's spontaneous, and it's able to do some useful work on the surroundings. And notice how now I've said useful work. It means it will apply some heat to the surroundings, which is what we've been doing. But it can also cause, say if it's a gas, to expand and push on the surroundings. So when we did our reactions, like reacting the magnesium and the hydrochloric acid, we could have maybe measured the delta G if we could catch all that hydrogen gas and get that hydrogen gas to push a piston and then to gather up the work that it did as well. It would be the heat and the work which would give you the delta G. But we let that gas kind of escape through the hole because we were only catching heat. We weren't catching the work it could possibly do. So if a delta G is negative, it means it is spontaneous. To chemists, that's important, the fact that we can determine it's spontaneous. And to engineers building engines and various things, it can do useful work. That's important to them because they can then determine how much it's going to push on a piston or something like that. That's the easiest way to think of it, pushing on a piston like an engine or moving a valve of some sort. If it's negative, it's non-spontaneous, and if you want it to happen, you must continuously put work into that reaction. Decomposition of water, you got to zap that, keep the electricity flowing so it decomposes. And if the delta G is exactly equal to zero, we've already encountered that. It's an equilibrium. It means the reaction is proceeding both in the forward and reverse directions. So like I said, if you take a look at your thermodynamic data, which is turning out to be a useless document, you'll find that the third column says delta GF, the Gibbs energy of formation. How much heat and work does it take to form those particular chemicals? And we can have the same equation that we use to find delta H and delta S. We can add up those Gibbs energies to get the Gibbs energy of formation for that particular chemical, all right? And for various reactions. The difference is this equation can be catered to whatever temperature. You can ask the question, how much Gibbs energy is going to be available at 30 degrees Celsius, negative 250 degrees Celsius, positive 500 degrees Celsius. You can shift it around. The table are the Gibbs energy of formation at 25 degrees Celsius. So these are locked into a particular temperature. But it does allow us to quickly calculate a Gibbs energy for a particular reaction at 25 degrees Celsius, at standard ambient temperature. Same equation. We're not learning anything new here, except the interpretation of it. So again, negative, the sum of the number of moles for the delta G of formation of the reactants plus the sum of the number of moles delta G of formation of the products, all coming off of our table. This is true at 25 degrees Celsius. Again, calculating is the same, it's just the interpretation. We know for delta H, right? If the delta H is positive, we say it's endothermic, right? If the delta S is positive, we say that it's becoming more disordered. If the delta G is positive, we we say that's a non-spontaneous reaction, and it's going to require the input of energy in order for the reaction to take place. So it's just in the interpretation of our numbers, and the interpretation comes from the definition of these terms, right? I have 3 examples here, but no need to do all 3. You know what? We just did this reaction here. Let's forget about that. We've looked at this. Let's just do the bottom reaction. Let's just do the last one. We've looked at water changing from gas to liquid. We've looked at the... This was a note that every year I debate on how I want to teach this, which is why I trip over it all the time, because I don't know my timing in terms of how long it's going to take me to teach it. And what I did one year is I simply just cut and pasted these from previous examples, obviously. And we've done this to death. Let's just do this bottom one. And then interpret the results. The reason you do 2 is to get a delta G that's positive and a delta G that's negative, so you can interpret the both. But it's a pretty straightforward interpretation. So this is number 3, and this is 2 moles, just to make sure that someone doesn't put 3.2 moles. Thank you. And I will try to put this on the smart board. I'll put it above. Delta G equals. So, negative. You're going to tell me something's not on that table, aren't you? What isn't on the table? The first one? We've looked that up already once, didn't we? Jeez. Is that the only one that isn't there? The thermodynamic table sucks. Theta. I'm losing it. Losing my mind here. What do we want? But we need it for delta G. Oh, and you know what? I've got that table somewhere. Yeah, I do. Right here. CaO. CaO, it doesn't have the Gibbs energy on it. Yes. What do I want? I want... Oh, man. Gibbs energy of formation of CaO. Boom. Do I know that that's a Gibbs energy? It just says calcium oxide solid 603. Let me just take a look at what the delta H is on it. Is it the same as the delta H? No, it's not. I'm going to assume that that's correct there then. 603.3. Delta G formation for CaO 603. And what's the sign on it? Negative. 603.3, and that is kilojoules per mole. It is in kilojoules per mole. I can just see it. We'll be getting into the middle of the test, and you'll all start to giggle, because I will have not given you the appropriate data. I have to make sure that that doesn't happen. All right. The calculators are making their familiar sound, which means you've acquired all your data. Somebody get me up to speed here. 2, and what is it for NH4Cl? You just read your numbers off that you've got in here. 2, you got 210. Okay, what do you got? 0.9, and then we've got a CaO, and that's our 603, right? Negative 603.3, and then we got to close the brackets up because that's all negative, and I need the CaCl2. 748.1 plus, what do we got for water liquid? 237.1 and what? 16.5. Close that up. Pardon for all the stuff. So again, calculate the one, calculate the other. Don't try to jam it in the calculator in one shot. Negative. What do you got in there? And what do you got in there? What do you got? What's wrong? You got a problem? The equation isn't balanced? Holy moly! Oh man, there is 2 nitrogen on the one side. This thing isn't even balanced. What kind of garbage is this? So I need 2 here? I'm just missing the 2? I got 2 chlorines there and I got 2 chlorines there. I'm good for the chlorines. I just needed 2 there, don't I? What about hydrogen? Hydrogen, we've got 6 here and 2, and then we got the 8. It's just that. This is going on forever. A lesson that never ends. I'm supposed to be evaluated this year by one of the VPs. I'm glad it wasn't yesterday and today. And then I'd sit down and I'd say, that was all part of my plan. It gets them engaged by finding all of my purposeful mistakes. What do I need here? A 2 in front of this guy? All right, what do we have for the negative number in front? You got a total? Okay, well, what do you got for the total? But then I do want the others. That's it? Kilojoules per mole? Okay. For the whole thing. That's exciting. Almost at equilibrium. It's almost 0, because really we usually talk in terms of the hundreds. What do we have in here for the negative number? Like for this guy, it'll be a negative of a negative, but I just want to know the separate numbers. 1,000 and 0, 9.1. So you're telling me this is exactly 1,000? Oh, okay. Negative 1,000 and 1, 8.2. Thank you for... Man, that sarcasm really hurts. All right. So, after all that, we have to interpret it. Is this reaction spontaneous or non-spontaneous or at equilibrium? It's spontaneous. Spontaneous. Yep. Anybody else get 971.1? No? You might want to run it through again, just to be sure. Okay, let's get to the interpretation part here. Is this reaction spontaneous? Yes, spontaneous. Which means it will happen on its own, and it will produce some useful work, but not a lot, right? You're not going to use this reaction to drive your car home in any way. It wouldn't get very far. Well, it would take a long time to get anywhere because we're not getting a lot of energy from that particular reaction. But it is spontaneous. All right? If it was positive, it'd be a non-spontaneous reaction. You'd have to input energy in order for that reaction to go. And if we somehow figured out a combination to get exactly 0 at 25 degrees Celsius, which would be a combination of these numbers, it would be reversible, but that's not necessarily going to be the case, right? Because the numbers aren't set up to be 0. It's what they are at 25 degrees, right? Okay? So those are the 2 interpretations of the Gibbs energy. We will encounter it with a delta H and a delta S, where we're going to be interested in an equilibrium temperature, if possible, okay? And so we've seen those types of questions. A very simpler way of looking at it as well is at 25 degrees using the Gibbs energy of formation to determine that Gibbs energy for a reaction at 25 degrees. And then that will allow us to determine, say, at laboratory conditions, whether that reaction would be spontaneous or not, right? That's why we have standard ambient temperature and pressure. And that's why we put those numbers at 25 degrees. It essentially is saying, in a laboratory, at 25 degrees, would that reaction happen? And the Gibbs energy would tell you. Yes, it would be spontaneous. Okay? All right. So, yeah, we're not doing any more of this stuff. Are you kidding me? Whew. think we're going to cut our losses. The rest of the question sheet you can do, and then there are obviously thermodynamic review questions. Tomorrow will be a full review period because I choose it so, not by pressure from external sources. And yeah, you can obviously work on that. In the textbook, there is no Gibbs energy problems, all right? And so you've got that question sheet. It's pretty involved. And I'll tell you right now, for the last question, you need some thermodynamic data. And I'll find it in a moment, and you can write it down. Because, again, like I said, I cut and pasted this from old assignments that we used to use. And I liked number 8, use the Gibbs free energy to estimate the boiling point of liquid mercury, which means you need thermodynamic data for solid mercury, and that's not on your page. Are you kidding me? So in a moment, I will find you the thermodynamic data for solid mercury, and then you can do this question. But reading this question, this is the question. That's why I put that extra one on there for a problem, to determine, say, the melting point. This one's going to be the boiling point. All right? So I will find that data for you.